Bonjour à toutes et à tous. Welcome to our colleagues and friends from the International Committee. Welcome to Lyon. Donc, je vais vous présenter aujourd'hui, on a pu...
So I'm going to present a certain number of things to you. We've looked at the surface area, but now we're going to be working on the structural work with the emergence of new materials. I was supposed to give this presentation on my own, but my colleague Alain here is present, and he's worked with me on the cross-cutting examinations and analyses, so he'll be able to provide me with support. So my name is Pascal TROTTIER. I'm in charge of the company entitled PavExpert. I'm going to refer to the contributors to this analysis. They provided us with the analysis. We have Benoît Picot from GC2D Laboratory, René Toulou from the University of Limoges. I don't know whether you're here. And also Alain Hebling from CEREMA, with whom I worked on these tests. Now, within the scope of this subject, we focused on a certain number of deliverables, notably Phase 1, improving the interpretation of the monitoring methods for an accurate road pavement diagnosis. First of all, I felt that what was important was our knowledge and also the state of the art regarding the methods for measuring the structural aspects with a high yield. And next, we wanted to work on comparative tests in France so that we could better characterize our methods, the way in which we use all of the different materials. To summarize what was done on this first sector in the report, we can see very clearly that what was important was to get to know the different methods for structural characterization with different materials to measure the deflection. We also then felt we needed to look at the different indicators that exist, SCI, radius of curvature, etc. Then in this report, we went through the different types of software, the back calculation software, and also everything that interacted on the interpretation of the data with the variables, whether they're physical or mechanical. I'm making the most of this opportunity to say also, and I'm going to put on my hat as the person in charge of analysing the French roads, please note that we have a working group that focuses on the best use of certain methods in France so we can better characterise and interpret the use of data. And this will form the subject of an ELAM report. I wanted to say this. This is something that is going to be launched. Next, this is for the third section. And here I focused on the analysis of the state of the art, as I said. We've seen many new materials come to the fore for measuring deflection, but it was important to look at these materials because for the last 10 years or so they've been used internationally. We didn't want to start out from scratch for France. On the contrary, we wanted to benefit from the analyses that have already been performed so that we could then evaluate the best way in which we could use them in France in the future. So you have two photos on the screen. The right-hand device is a device that was developed by Greenwood. It's called the TSD. And then on the left-hand side, a few years later, you have the Raptor. The Raptor was developed by Dynatest. The name has since changed. And this enables you to use different materials for the characterization process, but you can examine the state of the network, in particular the secondary network that has its own specific problems. With the Raptor, for example, we can even go onto the very smaller roads in the inner city, whereas the other device is more appropriate for motorways. Now, the materials have different technologies that make it possible to characterize deflection. To summarize, the TSD doesn't measure the deflection, but it measures the evolution of the slope. And this means that we can have deflection measurements, whereas the Raptor, thanks to the lasers, enables us to measure the deflection over time with different lasers, and then we can characterize the length of the basin. What was very important as well in terms of the state of the art was to look at how these different materials evolve over time, because we're interested in particular in the technology. The first TSD, as I said, was announced a certain number of years ago, and we can see that even these pieces of equipment have evolved over time. and it's very important to be able to characterize them to see exactly how they've been improved over time. Here, as you can see on the screen, we already have the 4th generation of the TSD, and for the Raptor, we already have the 2nd generation, and Cerama acquired the Raptor in order to better understand how it functions and to benefit from this knowledge in France. Now that we're familiar with these technologies, we thought, okay, in what way can we use them? One point that is very important to note is the fact that we're familiar with the measuring constraints on the network. We often have dense traffic, so it's very important to protect the operators. Here, we're able to measure without any contact, and we can measure it during the traffic flow at up to 80 kilometers an hour. I think this is very good for certain networks, for motorways, etc. However, when we work with lasers, necessarily we have to work during dry weather days. In terms of the measurements, how can we use this equipment? Well, this equipment internationally is often used for following up the state of the network for management over time, also characterization and identification of homogeneous zones, weak zones. It means that we can work out the priorities, what are the areas that need to be focused on, and we can monitor the structural status, and we can use certain indicators to have a first indication of the residual state of the roads. I've looked at a certain number of international indicators. Very often they are calibrated on the FWD, and as we'll see further down the line, we wanted to look at this in relation to our French standard devices, the deflector meters and the curvometers. So these are the indicators for interpreting the data from the TSDs and the Raptors. Notably, you've got the service curvature indexes, the curve measurements, etc. But you can see all the different indicators that we came up with. We even went so far as to characterize the traction depending on the thickness of the asphalt layers, etc. This is something that exists at an international level and that enables us basically to analyze the state of the art. We were able to use these devices also to see how we could use them to interpret the state of our network. We used the Raptor, for example, and here the work was to compare the results with different devices and see if we obtained the same results. Notably, you have a report on what was done on the RN76, the national road, the measurements with the flash, and then the measurements with the Raptor. You can see what the trends are. We can talk about that in more detail afterwards if you wish. Next, I was able to capitalize on the use of the Raptor on a motorway network with a thick asphalt structure. Here we've got data from previously, and this enabled us to compare the trend to see whether it's identical or not. Here you can see that we vary the speed in order to see what the impact of the speed is on the measurements, and we can see that from this perspective we achieve results that are very, very similar, notably with a standard deviation that is very, very low. And hence I was able to say, okay, if we have a weighting coefficient, we get pretty much the same type of result as we've always achieved with the other types of equipment. If it could be like this all the time, it's fantastic. However, when we did the second test, we saw that we didn't achieve the same results at all. So at the end of the day, this is all very good. It leads us to a certain number of questions in the context of our analysis, and we suddenly realized that we didn't achieve the same type of results at all. Given the fact that the tests were not all done at the same time, and given that we didn't have all the same information on the structures, I really focused on the analysis of the measurement per se. I repeat, we were looking at the state of the art. Over time, thanks to this stage, we were able to then work on the tests using the information from all of the previous years to work out how we on the French network can use these devices and optimize them, and see how, compared with our previous tests, we could improve our knowledge with the different types of equipment. And so as a result, let me pass the floor over to Alain, with who I I organized these comparative tests. Thank you very much. Good morning, everybody. I'm going to give you a focus specifically on the tests that we carried out in the Alsace-Lorraine region in 2022. And these tests made it possible to compare two different types of equipment, the Raptor by Ramboll and also the TSD by Lavast in Germany. And this equipment is used by a company that is in charge of checking the quality of the pavement roads. So these different tests took place in the Alsace region. The loop is between Strasbourg and Colmar. The full itinerary covered 168 kilometers. We stopped a bit earlier, so the reality corresponds to 152. And we have different types of road pavements, quite rigid, but not only rigid. We have pretty much all the different types of materials. We have lots of structures that are relatively rigid, as I said. When it comes to, most of them are bituminous materials, but we do have a few semi-rigid sections and a lot of flexible parts as well. So over these 150 kilometers, you have different structures, and I'll go into a bit more detail now on the comparison. Because what I want to do is present one of the cross sections. It was section number 12, whereby we compared the measurements. And as you can see, it's very interesting. In blue, you've got the Raptor measurements. In yellow, or in orange, if you like, you've got the measurements performed by the TSD. It's very important for me to be specific here. What is presented here is the average for 5 time periods. That way, we're able to see results, because our aim here is to present the results for 120 kilometers. When you glance at this, you realize that the two values are different between the different pieces of equipment. We do not have the same absolute deflection level. Deflection is what I'm presenting here. We don't have identical deflection. However, we are capable of giving exactly the same information with regard to the state of the network. In other words, we've got certain sections that are more rigid, sections that are less rigid, some that are weak, some that are strong. We're capable basically of telling you what are the harmonious sections for both devices. This is what these tools were designed for, to analyze the network and to analyze the weak part, the strong part, and the areas that need priority. We're able to observe this time around that there is another indicator that is not maximum deflection, but it's the service curvature index, SCI. This is a bit more native. It's closer to what the TSD measures naturally, because it also measures the speed of the deformation. We have exactly the same gap or deviation between the values, which is not surprising, because deflection is one of the values, and this leads to the SCIs, or reversely so. But we always see the same trend. In other words, we're always able to identify exactly the same homogeneous zones from one device to another. However, we would note that the gap or the deviation, whether it's on this slide or on the previous slide, is not constant between the different values. And this is what we see for the most part on a more flexible road pavement. Here you can see the gaps between the different two types of device that are more similar. Here, it's a lot easier to correct one of the measurements in order to obtain the other measurement. And this is what will be presented to you afterwards. So for the more flexible structures, we realize that the values are easier to compare when we look at the absolute values. Here we presented the deflection of one of the devices in relation to the other, just to see whether we have correlation. You can see that for the first line, the main line, you have a curve that is pretty flat. These are very rigid road pavements, so it's not easy to get correspondence or a match for this kind of structure. But the more and more you reach out towards a more flexible structure, the more it's possible. The structure that I've chosen is the most flexible structure among these. It's a 40/100ths of deflection, so it's not as high as all that. However, this is where you've got the best correlation, in other words, 0.55. And this, I would argue, is low, because we'd rather have correlation above 8 or 9 when we set out models. But given the fact that these experiments are in situ experiments, I think we can safely see that we're starting to see a trend. We're starting to see something quite clear. So here, for example, you've got the Raptors measurement. We could have shown you the measurement with the TSD. It wouldn't have changed very much. However, you are able to see very clearly that there's a trend. It's important to indicate as well that these measurements were made with the two devices, one after the other, on the same day with exactly the same conditions. But the geographic location of the measurement and the point that we use to feedback the measurement is not as easy as all that. You have to imagine that we measure continuously and we provide the measurements every 10 meters. So how can we ensure that we're measuring in exactly the same place, that we're feeding back the measurement from exactly the same place? That was one of the difficulties that we were up against. And this kind of curve would not be the same, for example, if I'd measured 10 meters earlier or 10 meters further along the road pavement. So I would say this calls into question everything we're saying to a certain extent, but nevertheless, in the work that we're going to carry out in the future, we need to be very watchful as to the zones that we use for providing the feedback. We need to be capable of guaranteeing that we provide feedback for the same zone so that we're comparing what's comparable. We don't want to have any mistakes relating to the location. Nevertheless, as I said, the results do tend to indicate that there is similarity in the results achieved between the different devices. The next two slides, these are designed to illustrate the repeatability of this equipment. The repeatability is pretty good. The first repeatability that is presented here is for the section where we perform the measurement 4 or 5 times. And here you have the measurement in particular for the Raptor on one of the sections, where we're able to note that one of the areas has a level of repeatability that would seem to be excellent, whereas the beginning of the section enables us to have exactly the same type of signal, but not the same values. So we need to look at why there's a slight difference, but at least the signal has the same shape. What I'm showing you here is a bit more complicated to use, in that this is a very rigid section, and it's one of the limits for the TSD. When we know it when we're using the older generations of devices, generations 3 and before that, they find it a bit harder to measure on very rigid road pavements, simply because the Doppler sensor was not as sensitive as they are today. And also the sampling rate was lower than it is today. The sensors were 1 kilohertz sensors, but now they're 200 kilohertz sensors. The TSD that performed the measurement was the Labast TSD, the German one, and it's a 3rd generation TSD. So these results, these measurements, as is the case with all of the rest, you need to step back slightly. Today, if we measured with a TSD, a 4th generation TSD, probably the results would be different and potentially better for rigid road pavements. So the difference between a very rigid road pavement and a very flexible road pavement, based on the results that I showed you, do tend to illustrate what I've said. Here what you have is slightly more complicated. As I said, it's a lot harder to know what we can say about it. Maybe we've reached the limit of what the equipment is able to achieve. So we're going to have to continue with our work in the future, notably for road pavements that are more flexible. That way we'll be able to perform a comparison, because this kind of structure is also the kind of structure that we've got on a lot of our roads in France. Over to you to continue. Thank you very much, Alain. So just to conclude to a certain extent on these types of equipment, let me stress that this type of equipment can be used and the data can be used for monitoring the network. Of course, it all depends on how the values evolve, for characterizing homogeneous zones and also for working out where work needs to be done. It's important, as Alain said, to be very watchful, and it's the same for the LCMS. When you work on repeatability and the evolution of the data over time, you have to work on geolocalization. It's a real point that you have to be very careful of. What kind of equipment do you use? There are all kinds of technologies out there today, highly innovative technologies, but you need to make sure that you're able to characterize an element that is in exactly the same place. Next, as Alain said, we still have a bit of work left in order to be able to look at exactly how we can use this equipment on the different road pavements. Notably, these types of tests have enabled us to show the limits of this technology, and we now need to see how we can use this technology over time and maybe go into more detail on the analysis of the value itself. I haven't said this so far, but when it comes to the measurements in relation to the deflector graph, our reference equipment, we don't have enough reference materials. So I just wanted to say at least these tests did enable us to better characterize, to have a clearer idea of what we can do and how broad the scope is for the future. So thank you very much, everybody.